Okay. So where were we? So last time, we discussed the former rigorous definition of the limit convergence of the sequence. So it goes like this. So we say the sequence AN is converging to a number A, which is defined as for any positive number epsilon, we must be able to find a natural number and satisfy the condition. And just one more thing. So ST implies such that, such that. This phrase is so many used in mathematics, so we gave the symbol. ST means the such that. So we must be able to find a integer satisfying that for any term whose index is greater than this number n, then the distance between the limit of sequence and an is guaranteed to be less than the epsilon. So if we can find such an n for any positive epsilon, then we say the sequence is converging to A. Okay? Yeah. I remember that last time, so we tried to describe this by using the pictures. And today, as I promised, so we will need to study this definition, this time by looking at a non-example. So, okay, so I struggled to draw a picture. And this is a sequence. And, well, I tried my best to show that this sequence is not convergent. Actually, this sequence is somehow oscillating between this and that. So up and down, up and down, up and down. So this is not a converging sequence. So this is a non-convergent sequence. And we will see why this sequence fails to satisfy this definition. Okay. All right. Okay. All right. So okay. Maybe there's someone like me. So, well, and suppose that there is a student, and he or she is trying to claim that this sequence is converging to this number A. Okay. So that guy. So so that guy insists that just give me any epsilon, then I can find a integer satisfying this condition. So okay, so for that guy, I gave him this much epsilon. Okay, so then this is A plus epsilon, and this is A minus epsilon. And okay, for convenience, let me draw the picture. Okay, so this strip, the region between this line to that line is A minus epsilon to A plus epsilon. And in this picture, it looks like for this epsilon, it looks like I can actually find n. What do you think is my n? Yeah, 3. Because, when n equals 3, then beyond this point, all the other terms beyond this point, they're guaranteed to lie between this line and that line. A plus epsilon, A minus epsilon. All right? Okay. So, so it looks like I can find an n satisfying the condition for this specific epsilon. But you have to be really careful. In order to say that the sequence is converging to number A, then you must be able to find this number n for any arbitrary positive epsilon, right? Okay, so this time around, I gave the guy even smaller epsilon. This. Okay. Now, the distance of the line segment, length of this line segment is my epsilon. So this is A plus epsilon, and this is my A minus epsilon. Okay. Now we're going to see why this epsilon does not allow any such n. Okay. So this is this strip. This is A minus epsilon and A plus epsilon. And I can actually find infinitely many dots lying between this line and that line. This tube. So in this case, I'm really tempted to say that, in this case, my n would be 4. Am I right? No, because according to satisfy the condition over here, then every terms beyond this point must be between A minus epsilon and A plus epsilon. But well, even though I can find couple of points that lies between this line and that line, but I can still find another bunch of points which lies which is not between A minus epsilon, A plus epsilon. Okay. What if I increase my n? Suppose that my n is not 4. If my n is like 11 or 13, but in that case, no matter how large your n is, you can never be able to find such an n for this specific epsilon, right? Therefore, this sequence, well, for this specific epsilon, you were not able to find the number n satisfying the condition. Therefore, this sequence is not converging to number 8. All right? Well, as a matter of fact, this sequence is not converging to any number. Okay, so this is a diverging sequence. So this is our definition of the limit and epsilon limit and an argument. Okay, so the point is, so if you want to say some sequence is converging to some number, then you should be able to find number n for any positive epsilon. So in other words, if you can find any epsilon, and that does not allow an integer n satisfying the condition, then your sequence is not converging to A. Okay. Great. This was actually the greatest hurdle in freshman calculus. Are you good? Any questions? 혹시 질문 있으세요? Okay, if you're good, then I believe you're 50% done in this course. Okay. So this argument of the argument like this appears so many times in this course, and if you're fine about this step, then I think you are having really great start. Okay. Now let me turn to even more specific example. I want to prove this. My intuition says that this sequence must be converging to number 5. But that is merely my intuition. So as a mathematician, so I must be able to give the formal proof of why this sequence is converging to 5. Well, using the epsilon and n argument. All right. Yeah. obviously the sequence is my AN. So in order to show the sequence AN is converging to 5, then I need to show that for any positive epsilon, I must be able to find a integer n satisfying the condition, blah, blah, blah. So to do that, so I will need to do a preliminary analysis before I give you a formal proof. So this is a preliminary analysis. So this is some sort of a reverse engineering. So, okay, well, why is that? So, in terms of definition, now for any epsilon, I will need to find the number integer n, satisfying the condition. But for the preliminary analysis, I will start from this inequality. And I will try to find the condition that for which n this inequality is satisfied. If I can find such a condition, then maybe I can find that will help to find this n. All right, okay. If you do not understand what I'm saying, okay, just follow me step by step. Well, this is my sequence AN, and this implies the distance between the sequence and the limit. And 5n over n plus 1 minus 5. So this is 5n minus 5n plus 5 by n plus 1. Okay? And this guy, they cancel each other. So 5 over n plus 1, absolute value. Well, okay, in this case, they are all positive numbers. So yeah, I don't need them. Okay, so this is the distance between the sequence and this limit. And we require that this number must be less than epsilon, right? In other words, under which condition this inequality is satisfied? This is the question that I am looking to. Okay, so in order to answer the question, I will need to solve this final inequality for letter n. Okay, this is not a hardcore analysis. Yeah, it looks like the answer is very simple. Okay. Aha. Okay, so that means if the index of term is greater than this number, then this inequality is satisfied. Right? Now this gives me idea. So because of this, so if my index is greater than this number, this inequality is satisfied. That means my n would be if a number integer with greater than this. If my large n is a integer greater than this number, then I am pretty sure that this inequality is satisfied. Therefore, that means I can find this n satisfying the condition for this epsilon, right? But however, in this case, well, I didn't say specific. I did not impose any condition for this epsilon. Therefore, I am okay to say that for any arbitrary positive epsilon, I was able to find the large n satisfying the condition. So the proof is done. Okay. Okay. Yeah. I know there is some of you do not understand what I'm talking about. So okay. So now this is time to give you the rigorous proof of the statement. Okay. Now this is the formal proof. choose any epsilon. For any epsilon, then we choose our integer, large n, to be any positive integer that is greater than equals to 5 over epsilon minus 1. Well, okay. Now, okay, so for this epsilon, I have chosen my n. Now, what I need to do is, if this small n is greater than this number, then I will need to verify that an minus 5, the distance, this guy, is less than this epsilon. Okay, but this is somehow very obvious. If my n is greater than this n, then an minus 5 is because of this computation, we know that this one equals to 5 over n plus 1. And, well, n is greater than this large n. Therefore, but now this n is in the not numerator but denominator 분모. n이 분모에 있기 때문에 this guy must be larger than this. Okay? And this is, again, so this is greater than this, then this one is also in the denominator. So this whole number must be even greater than equals to this number, okay? But this is what? Simplifying this is just epsilon, right? Okay, so my proof is done. For any epsilon, I was able to find the number, large n, satisfying the blah, blah, blah condition. Right? Good? 괜찮아요? 여러분 거기 그러니까 이해가 안 되시는 분들이 분명히 있을 것 같은데, 그러니까 전혀 부끄러운 게 아니고 매우 자연스러운 현상이거든요. 그러니까 혹시 옆에 있는 친구들은 다 끄덕끄덕하고 있다 한번 이해를 못하고 있는 그렇게 생각할 필요 없이 그냥 조금만 생각하면은 이해할 수 있어요. 예. 제가 I'm gonna show you just one more example. Okay, another obvious exercise. 1 over 2 to the power of n is tending to 0 as n goes to n to the infinity. Well, as always, yeah, I will give the name for this sequence. This is my an. Well, again, I will begin from the preliminary analysis. The reverse engineering. So I am looking for the condition of n so when, under what condition the limit and the sequence is less than the epsilon. And well, in this case, this is just easy. So, which is this, right? Well, I do not need these absolute values. And I require that this guy is less than epsilon. Okay. So all I need to do is, okay, solve this last inequality for letter n. This is what? So n must be greater than negative log the base 2 log of epsilon. Right? Okay, but just one tiny little thing. Yeah, I know all of you guys understand what the log function is. Logarithm is, which is the inverse of the exponential functions. But however, well, in this course, technically, I have not introduced neither of the logarithm functions and the exponential functions. So at this point, I cannot use the log functions, especially for any arbitrary positive number epsilon. So just forget about this logarithm function for now. So since we cannot use the log function, we cannot officially use the log function for now. So I will try to use just one little trick. Comparing 1 over 2 to the nth power and just 1 over n, which one do you think is greater? Yeah, obviously this guy is greater than this. How do I know that? Because we know this. Actually, if you're pursuing 100% mathematical rigorosity, then well, you can try to prove this by using mathematical induction. But I won't. Just take this for granted. And we require that this guy is less than epsilon. Okay. All right. Now solve this final inequality for n. Then this is n is greater than 1 over epsilon. Okay. Okay. So this is at the end of my preliminary analysis. Now I will give you the formal proof of the theorem, the formal proof of the exercise. For any epsilon, we choose our n to be any number greater than 1 over epsilon. Okay, now I will need to see that if any number greater than this guy, any integer greater than this guy, so if small n is greater than this number, then an minus 0 must be less than epsilon. So if this index is greater than large n, then an minus the limit of sequence, which is 1 over 2 to the power of n. But we already know that this guy is bounded by 1 over n. And since we are assuming that index is greater than this number, so this is also bounded by 1 over large n. And since also we do have this inequality, which is epsilon. Okay, so the conclusion is for any given epsilon, if we choose our n to be this guy, then if the index of the term is greater than this number, then the distance between this term and the limit of sequence is guaranteed to be less than epsilon. Okay, so for any epsilon, we were able to find the integer n to satisfy the blah 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 condition. So the proof is done. Okay, good. Yeah, good. I think you guys are actually doing really great job, especially for this semester, because well, comparing to my previous year's experience, well, when I was done about this part of the lecture, then like 90% of students got puzzled. But I saw some of you are nodding. Yeah, I think this is a really great sign. Thank you. Okay. All right. So technically, from now on, whenever you want to try to show that any sequence is converged to some number, then you are supposed to do this kind of analysis every single time. Yeah, that sounds really painful, right? So this time I will need to introduce you to save you a lot of effort in doing this sort of exercise. So what is this? Yeah, this one. Yeah, I just ran out of space. I have two sequences, A and Bn, and suppose that An is converging to number A and Bn is converging to another number, say B. And if you know that these two guys are converging sequences, then An plus Bn, the another sequence, which is made by, which is given by adding every term, summation of every terms. And this sequence is converging to A plus B. And An times Bn, this is another sequence, which is also given by taking a product between two terms, corresponding terms. Well, this is also converging to AB. And if An is, A is not 0, and if A is also not 0, then this guy is also converging to 1 over A. So these three theorems, these three statements will actually save you from lots of analysis like this. Why? Because whenever you can show that any two sequences are converging, then you can actually make up many different sequences from these two sequences. And for that cases, you don't need to actually prove anything because of the theorem. Okay? Yeah, I know this is very triviality, but yeah, just one last thing. Yeah, but this is so obvious. Yeah, I don't need to justify it. All right. So how do I prove this letter A, B, and C? Actually, these three statements. So these three statements were taken granted when we were high school students, right? So we just used it free, without any justification. The proof of A, B, and C, they are actually far from triviality. This will actually require a lot of effort. I'm gonna leave the proof of B and C as a homework exercise, and I will tell the TAs that please do the proof of B and C in the recitation sessions. And for today, because I'm running out of time, so I will only give you the proof of letter A, the easiest one. Sorry. Choose any positive epsilon. Okay, so this is my goal. An plus Bn is converging to A plus B. And well, in order to show this, and these are two hypotheses given from this theorem. So I will need to take advantage of these two conditions, right? And since An is converging to A and Bn is converging to B, therefore, for this given epsilon, I must be able to find an integer, which I will say n1, such that satisfying the condition. If n is greater than n1, then an minus an is less than epsilon. Yeah, I should be able to find such an n1 because this one is converging to A, right? And also since Bn is converging to B. So therefore, for this given epsilon, I also must be able to find another integer, positive integer, which I will call n2, such that if for any index greater than n2, then Bn minus B is less than epsilon. For this one single epsilon, I could find these two integers. Okay, but our goal is we need to show that this guy is tending to A plus B. So for this epsilon, we want to choose that our n is between these two integers, n1 and n2, there must be one integer which is greater than or equals to the other, right? That number I will call n. Choose the greater one between n1 and n2. Then what happens? Then if the index is greater than this number, n, okay, now I will need to see the difference between this guy and that guy. And an plus bn minus a plus b, right? But yeah, I will rearrange the order. An minus a and plus bn minus b. Am I good? Now it's time to use the triangle inequality. So an minus a plus bn minus b. This single absolute value is bounded by these two, sum of these two absolute values, right? This is the triangle inequality. Okay, now what? Our index n is greater than this number. So that means my n is at the same time simultaneously greater than n1 and greater than n2. Right? Right? So since my n is greater than n1 and greater than n2, therefore this inequality is true and this inequality is also true. Right? So this is less than epsilon and this is less than epsilon. So everything is less than 2 epsilon. Something is not right, right? In order to be the right proof, this guy and this guy, they must be less than just not 2 epsilon, but they must be epsilon less than epsilon, right? So, this one does not really go. Actually, this is a right proof. So I will need to fix this scenario. How? Okay, first I have chosen epsilon. But, well, now since they are converging to A and B, so instead of using this naively using this epsilon, I will try to divide this epsilon by 2. So epsilon over 2. For that given number, epsilon over 2 is still a positive number, positive real number. Therefore, for not epsilon, but for epsilon over 2, I must be also able to find integer n1 and n2 satisfying the condition. But in that case, I will need to change this. Right? Because, well, this is by the definition of the limit of sequence. For any positive number, you must be able to find some integer satisfying blah, blah, blah condition. So this time around, I have chosen not epsilon, but epsilon over 2. For that positive number, but I can still find n1 and n2. Right? So, okay, now the rest of the rest of the proof is exactly the same thing. For this epsilon n1, sorry, for this n1 and n2, my n is this one, the n. Then, well, right? So this is epsilon. Okay. Yeah, yes. Uh, well, yes, this is kind of, well, so our convention is, so whenever your proof says that the an minus a is less than some constant times epsilon, then we consider that it's completely rigid proof because we can still use the technique, right? Okay, so I wanted to say that what I mean by an, the difference between an minus a is less than epsilon. So that, well, in our daily language, so I can translate as something like this. So you can make the difference between a and an arbitrarily small. That is what I mean by an minus a is less than epsilon. Epsilon usually refers to a really tiny small number. Just any arbitrary tiny small number. But if you're 100% sure that an, the difference between an and a is less than that tiny arbitrary small number, then we say that your sequence is converged to that number. But that arbitrary tiny small little number, the idea of this arbitrary tiny little small number doesn't change too much. Okay, whether or not you multiply by some constant. So, well, in the exam, well, if your proof ends up with some constant times epsilon, that is good. Yeah. Does it answer your question? Yeah, good. Yeah.
Actually, given epsilon is very small, so we can kind of ignore the constant that is multiplied by epsilon. So can't we just finish our proof by just ending the right side to epsilon? Okay.
Yeah, you're completely okay. Yeah, you can still do that. Yeah.
Good to see.
Right. Yeah, because we are the beginners. We are learning, so we are at the first stage of the learning curve. Yeah, so this is why I am trying to do this. But later on, maybe from time to time, my proof will just end up with some constant times epsilon. Okay, but that is still good. Okay, yeah, good point. Thank you. All right. For questions for letters B and C, yeah, I will leave them as exercises. And what's next? The squeeze theorem. Let us consider the scenario. I have three sequences, AN, BN, and CN, and it happens to be the middle sequence BN is lying between AN and BN for every index n. And also on top of that, let us assume that the right-hand side sequence and left-hand side sequence, they are converging to the same numbers, A. In that case, this middle guy is also converging to the same number. This is the squeeze theorem, or sometimes called the sandwich theorem, whatever it is. Let's prove this. This is our goal. So we are supposed to show that this sequence is converging to A. given that this guy and that guy converging to A. Okay, so let us prove this. Okay, just choose any epsilon. And AN is converging to A. Because of that, I can find a number which is N1 satisfying the condition. So what condition? So if for any index that is bigger than N1, then AN minus A is less than epsilon. And same thing is true for the another sequence Cn. So I can find another integer, positive integer N2, such that if N is greater than N2, and Cn minus A is less than epsilon. Okay, good. But this time, I will try to rephrase these two inequalities. So, well, this is A minus epsilon is and A plus epsilon. And okay. Oh, sorry, not B, C. Yeah. Okay. Yeah. So if this index is greater than N1, satisfying this inequality, so which is mathematically the same as these two inequalities holds at the same time. Okay, and also this inequality is true means these two inequalities hold at the same time, right? So okay. Right. And since this inequality is true for all indices greater than this number, so therefore, yeah. Sorry, my notation is somehow messed up. Yeah. So this time around, let me try to find not N and M. So we let our M is an integer, which is the largest integer among these three guys. So N, yeah, they already used my favorite letter N. Yeah, I'm really sorry about that. Yeah. So N, N1, and N2. Among them, you choose the greatest one. That is gonna be your M. Okay. Okay. Now we will see what happens if my index is greater than this number. If M N is greater than this number, then okay. So if my index is greater than this number, then these two inequalities are true, right? And these two inequalities are also true, and these inequalities are also true. All these inequalities they hold at the same time if my N is greater than this number, right? So since this guy is true, A minus epsilon is less than AN. So therefore, this inequality also must be true, right? And this inequality also must be true. And these inequalities also must be true, right? So AN, BN, CN. Okay, now combine these inequalities one by one. So therefore, A minus epsilon, which is less than AN, and BN, CN, A plus epsilon. So therefore, A minus, so this, the middle sequence BN lies between A minus epsilon and A plus epsilon. And rephrasing this, this is exactly same as AN minus, so BN minus A is less than epsilon. Right? Okay. Cutting to the point, for any given positive epsilon, I was able to find some integer, positive integer m, and if your index is greater than this number, the distance between Bn and A is less than the epsilon. So this implies Bn is converging to A. Right? Good? Okay. Great. Before I end this section, yeah, I will introduce a very silly theorem. Suppose that I have a sequence AN, but say that the absolute value of AN is converging to 0. Then the original sequence AN is also converging to 0. Okay, which is very obvious, but I'll try to justify the theorem like this, because minus absolute value of AN and plus absolute value of AN, they are going to be the upper and lower bound of sequence AN, right? And since this guy tends to 0, so this sequence tending to 0, and that sequence also tending to 0, therefore the middle guy should be tending to 0. Okay. All right. The next one. Yeah, yeah.
We can show that n is much bigger than n1 and n2.
You want to show that? So yeah, I'm not pretty sure that I understood your question properly, but you're asking that m, this number, must be greater than. Okay, maybe we can discuss it later. Yeah. Okay. Okay, so where was that? Yeah, approximation of square root of 2. So do you know how to approximate square root of 2? Well, without using calculator? Yeah. So many decades ago, so when I was high school student or the middle school student, I don't remember correctly, but my teacher told me like this. This is how you approximate square root of 2. So, well, first, just start from any number. Just choose any number you want. And then the number, and what you're supposed to do is, you take the reciprocal of the number and multiply by 2. And you take the average. Then you're going to get another number. And if you repeat the process on and on, then eventually your number will be tending really close to square root of 2. So this is here. This was her idea. Okay, so I will rephrase her idea into a recursive relation of the sequences. Suppose that we want to approximate square root of 2. Not just 2, but square root of any positive integer, p. If we want to approximate square root of p, and p is obviously a positive number, then Sn plus 1 is the average between Sn and p over Sn. S1, so, well, this is what we call the recursive relation of the sequence, or 점화식, right? If you remember correctly in Korean. In order to, first, if you want to use this recursive relation, then you will need to have a starting point, which is S1. You choose S1 to be any number you want. So her idea is maybe we can, her idea was maybe just choose our P to be 2. And our starting point, S1 to be, say maybe 2. Then this is 2. So if P is 2, then S1 is 2. From 2 plus 2 over 2, which is what? So S2 is what? Just 1.5, right? And now we plug in 1.5 to this recursive relation just one more time. So 1.5 plus 2 over 1.5. Divide everything by 2. And what is that? Yeah. I don't know. Yeah, but I believe that number will be 1.4 something, something, something. So and if you plug in that number into the same recursive relation and on, then for each time you make an iteration, then your iteration will be getting better and better, and eventually will be tending to square root of 2. Okay, isn't that amazing? But my question is, how is that possible? Okay, how can I justify this recursive relation and her claim, that which is tending to square root of 2? Yeah, so I'm going to show you how. Okay, since we were talking about the case when P is 2, so P is 2 and S1 is 2. Then our recursive relation is going to be okay. First, I will make use of the arithmetic and geometry inequality. This is our Sn plus 1. Sn plus 1 is defined to be the average between Sn and 2 over Sn, right? But because of according to the age inequality, the arithmetic mean is always greater than or equals to the geometric mean of these two numbers. And in this case, these two numbers involved, I'm pretty sure that they are all positive numbers, right? So this is their geometric mean must be Sn times 2 over Sn, and which is square root of 2. Okay? So no matter how hard you try, but your Sn, your sequence, is always a number greater than or equals to square root of 2. Okay? So cannot be less than square root of 2. Okay, now, how close Sn to square root of 2? This is very important question. Yeah, okay. So how close that means in mathematics? So we want to consider the distance between Sn and square root of 2. But in our case, this guy is guaranteed to be greater than or equals to square root of 2. So yeah. So in this case, it's good to get rid of these absolute values, annoying absolute values, because this guy is always greater than or equals to 0, right? And Sn plus 1 is just Sn, the average of Sn and 2 over Sn, and minus square root of 2. So I will need to do just a little bit algebra here. So 2 Sn and Sn squared plus 2 minus 2 times Sn square root of 2. Okay. Okay. Yeah. Okay. Good. Yeah. Did I make any mistake? No. Yeah. I guess this is good. Looking at these parentheses, I feel like this is a perfect square of some binomials. Right. So this is just 1 over 2 times Sn and Sn minus square root of 2, everything squared. Okay. So I'm going to rearrange the order of these factors. Sn minus square root of 2. But this Sn is now being absorbed to the second factor. And let's see. This is 1 minus square root of 2 over Sn, right? But you know that Sn is always greater than or equals to square root of 2. So this number is always less than or equals to 1, right? So this entire thing is less than 1. Therefore, this is 1 over 2 times Sn minus square root of 2. Right? Because this number is less than 1, so this guy must be bigger than this. Okay? Okay, good. Now what? Oh, okay. All right. Okay. Oh, good. Thank you. Yeah, I lost the track somehow. But yeah, now I'm good. So we realize that this guy is bounded by this number. Okay. Now, for this factor, okay, let me just ignore this 1 over 2 for now. But just for this factor, I can repeat this exactly same procedure just one more time. Then is 1 over 2 times another 1 over 2 and Sn minus 1 minus square root of 2. Yeah, index decreases by 1, but at the time, I will obtain another additional one factor of 1 over 2. Okay, yeah, so maybe this is much better. Okay, and I can repeat the procedure just one more time. Right? And eventually, I will end up with 2 to the nth power S1 minus square root of 2. Right? But what is my S1? Oh, yeah, I forgot. Yeah, S1 was 2. Oh, good. So 2 minus square root of 2, which is obviously less than 1, right? So everything is bounded by just 1 over 2 to the power of n. Okay, so consequently, the difference between the term Sn plus 1 and square root of 2 is bounded below by 0 and bounded above by this number. Now, this is time to make use of the squeeze theorem. Because of the squeeze theorem, this middle guy is tending to square root of 2. Isn't it great? Yeah. Okay, now I recall well. Yeah. It's been almost 40 years ago, but I still admire her inspiration towards the computer approximating the square root of 2. This is so nice. And I really like this iteration because it tells us the difference between our iteration and this is my approximation, and this is a true value, right? The difference between my approximation and true value is getting smaller, not polynomially, but it's getting smaller in an order of exponential function, right? So, well, in terms of computer science, well, if you repeat this procedure on, and every iteration, you're going to get your approximation is getting better and better by digit. So every iteration will become one accurate digit. And this is so nice approximation. Because there are some, from now on, we're going to see many interesting approximations in this course. Then some iteration is not decreasing by the order of exponential function, but some iteration is decreasing order of some polynomial function, one over some polynomial functions, rational functions. In such an approximation, it's almost useless because, well, if you have such an approximation, that means sometimes your 1 million times approximation is not enough to guarantee one accurate digit. But this is so nice. Okay. Good. Okay, now the next section. And we will talk about the monotone convergence sequence. Monotone sequence. A sequence is called increasing sequence if an is always less than or equals to an plus 1. So sequence is, sequence is getting bigger and bigger. And decreasing if an is greater than or equals to an plus 1. And a sequence is monotone if either increasing or decreasing. Okay. Yeah, they are just terminologies. Okay. Good. Increasing and decreasing and monotone sequence. And another one. A sequence is bounded if all numbers in the sequence is contained in some interval minus b to plus b. So usually b is chosen to be some large number. But anyway, so that means your sequence bounded means your sequence is not belonging to positive or negative infinities, right? Okay, so your sequence may be oscillating. So okay, but not every bounded sequence is convergent, but well, okay, so you know what I mean. So you have the idea. So not goes to not getting arbitrarily large or not getting arbitrarily small. So and bounded above means slightly relaxed condition than the boundedness. If your sequence is bounded above, then your sequence cannot exceed some certain point. Well, in that case, if your sequence is bounded below, your sequence is still allowed to go to negative infinities, okay? But cannot exceed some point, and bounded below, same thing. Yeah. Your sequence may increase to go to the positive infinity, but cannot be less than some certain point. Okay. And every convergent sequence is bounded. Not every bounded sequence is convergent because, well, you can still imagine a oscillating sequence, which is not convergent, but that it must be bounded. But for the other side, if your sequence is convergent, then I am 100% sure that my sequence is, in that case, bounded. Why? This is still obvious, but well, that also requires some proof. We suppose that AN is converging to A. So since my sequence is convergent, so for any epsilon, I can find an integer large n satisfying the blah 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 condition, right? Okay, so instead of choosing any arbitrary epsilon, this time I will set my epsilon to be some fixed number. Well, just say 1, yeah. For this epsilon, I must be able to find an integer, I would say n0, such that if n is greater than this number, then an minus a is less than epsilon. In this case, epsilon is 1. Okay. Okay, so so I'm going to draw a little tiny cartoon just to describe the situation. I have this is a convergent sequence, and this is the limit of the sequence, and this is a minus 1, and this is a plus 1, right? So beyond this point, every term beyond this point must be lying between a minus and a plus 1, right? So we choose that our m is and m is maximum of so what is this? So beyond this point, so all terms beyond this point, they lie between a minus and a plus 1, right? So therefore, choose the greatest guy. So, well, that means before this point, I only have the finitely many terms, right? This many terms. So for these finitely many terms, you choose the greatest one. Greatest one between a plus 1 and these guys. And you choose the least one, a minus 1 and these finitely many guys. Then every every term in this sequence must be bounded by small m and large m, right? Because these infinitely many terms, they are known to be bounded by a minus and a plus 1. So all we need to do is just find the greatest one in this finitely many terms. And comparing with a plus and a minus 1, and we are sure that all the terms in this sequence is bounded by small m and large m. Right? I believe this is the most important theorem in today's lecture. But I am running out of time. But I will try my best to explain this. This one is called monotone convergence theorem. Oh, yeah, I messed up. Yeah, not this one. Yeah, sorry. Yeah, this one. An increasing sequence that is bounded converges to a limit. So you suppose that you have an increasing sequence, but we are assuming that sequence is bounded. The sequence is bounded means your increasing sequence cannot exceed some certain point, but still increasing, right? And our intuition says that in this case, my sequence must be converging to some point, right? Because increasing but cannot exceed some point. So therefore, it must stabilize underneath that limit, right? So this is the idea of the monotone convergence theorem. What do you think? Do you agree? Does it sound reasonable enough to you? Yeah? Okay. But I will give you proof of this. Okay. Say that AN is an increasing sorry, yeah. I only have 2 minutes, and I do not really want to rush this theorem. Yeah, so let's say this is for today, and see you next time. Okay, thank you.